So in the last lecture, we have discussed, we started with the discussion about physical pendulum, so and angular harmonic motion. So we'll discuss more about that. So let's quickly go through the concept of angular harmonic motion and the example of the physical pendulum once more. We saw that it is an angular oscillation such that the angular displacement from the mean position is an harmonic function of time. So okay, so the displacement is in radians, as is the amplitude. Okay, rest of the things are the same. Omega is 2 pi f, or 2 pi divided by time period in radians per second. It's called angular frequency. And phi is the phase constant in radians. Okay, so this is something that we have seen in the last lecture. Okay, so just making a recap of this. Now from this, we get the dynamical condition for angular harmonic motion, and that condition is a condition on the torque we saw. Okay, so this is the angular velocity, and double differentiated, and we get the angular acceleration. So we get this condition that angular acceleration is directly proportional to angular displacement and opposite in direction. So this tells us that the net torque would be equal to this type. So this here becomes the dynamical condition of angular harmonic motion. There is a net restorative torque which is proportionate to angular displacement. Okay, so once again, this is part of what we have discussed in the last lecture. Now we had seen the physical pendulum as the main example, but it is doing angular harmonic motion, or it performs angular harmonic motion under a special condition, and that is that the angular displacement should be small. So let's take a relook at that. So physical pendulum, angular harmonic motion for small angular displacements. Or in short, these are just called small oscillations. So what this means is that the angular displacement, the maximum angular displacement, should be small enough that we can do the small angle approximation. That basically means this approximation can be done. So we had seen that if you have a pendulum of any shape which is suspended, or a rigid body of any shape which is suspended from the point P, such that its center of mass is C, then this is the equilibrium position. There is an axis at P. So the moment we take it from the equilibrium position to an angular position, such that this is happening, now we can see that if it's at an angular position theta, and this distance is d. Piyush, you have the part that I've written above now, it's a repeat of it, it's a revision of what we did in the last lecture. So I don't think you need to note down all the points, okay? But yeah, I'll take you back to that. You can just go through some of the things once more, okay? Even this thing, we have discussed in the last lecture. I'm just revising. Then we'll look at examples based on this. So in this position, at an angular displacement of theta, you can see that the net torque, now this theta is, you can see the diagram anti-clockwise, whereas the torque this will provide will become clockwise. Okay, so this is a clockwise torque of mg d sine theta, which we can approximate as mg d theta for small angular displacement. Okay. Approximate it is this. So you can see that the torque is opposite to this thing. So when we substitute torque is equal to I alpha, here alpha will be minus of d2 theta by dt square, because theta was in this case anti-clockwise, and the alpha we are getting will become clockwise. So we get the angular harmonic equation straight away because I've already used the small angle approximation. So I get d2 theta by dt square is equal to minus of mgd divided by moment of inertia into theta. But of course, this is for small angular displacement. So omega square becomes this standard formula, and time period therefore has the standard formula. So all we need to do is understand the moment of inertia about the point of suspension or the axis of rotation and the distance of that axis from the center of mass. These two things are needed to calculate the time period for any physical pendulum. Okay, so I'll just scroll up and take you to the previous section once. Okay, and just go through all these points. If there's anything you need to discuss, just let me know, especially Piyush. Okay, so all these points are clear now? Right. Okay, now let's come to the physical pendulum. So it's basically rotational mechanics. As you can see, you're just applying the concept of pure rotation about a fixed axis. But there's that added thing that the angular displacement is small so that you can approximate sine theta as theta. So we are approximating sine theta as theta. Yeah, but Jagannath, this is a condition which I've just mentioned again over here, no? That I should be able to approximate sine theta as theta. So for that, theta should be small. By small, we mean that in degrees, theta should be less than about 5 degrees. Okay, but remember, of course, theta will actually be substituted in radians. So from trigonometry, if you remember, for small angle, you have the approximation that sine theta becomes equal to tan theta, becomes equal to approximately theta itself in radians, and cos theta becomes approximately 1. So those are your small angle approximations. I'll just write them on the side over here. Small angle approximations. That sine theta is approximately equal to tan theta, becomes approximately theta, and cos theta becomes approximately 1. So here theta should be expressed in radians. Okay, so Jagannath, hope this is clear, the small angle approximation concept. So the thing is like, yeah, of course, what happens if we give a large angular displacement? So it will still oscillate, okay, because it has the mean position and there is restorative torque. But that oscillation will not be harmonic. Okay, then it will become some other type of curve. The theta versus time will become some other type of curve. That is the only difference. Okay. Right. So let's look at an example. So now, like, it'll be a little bit about application of rotational mechanics concepts. Okay, so let's get something typical. So I have this L-shaped object, which I have suspended from a hinge over here. So this side length is L, this side length is L, and total mass is equal to M. So it is an L-shaped rigid body, which is basically a rod, a thin uniform rod of mass M and length L, rather length 2L, which is bent into a 90-degree angle. Okay. So this L-shaped rigid body, it is hinged. So it can rotate freely. So we have to find the time period for small oscillations. Small oscillations means that small angular amplitude. So as you can see, it becomes a rotational mechanics problem ultimately. Okay. Bit of center of mass also. You have to find the distance of the center of mass from the point P, and you have to find the moment of inertia about the point P. So just try this out. This is a core mechanics problem now. Okay, it's the SHM part is just the formula. Time period is square root of mgd divided by moment of inertia.
So can you scroll up, please?
Yeah. Okay, done.
No, sir, wait.
Yes, sir.
Okay.
The split, sir.
Actually, even this part you have in last time's notes. Okay, so just make sure you understand the steps. So basically, torque is equal to I alpha. Moment arm you can see for that mg is d sine theta, which will approximate as d into theta, because we are assuming a small angular displacement. Okay. Now try out this question. It's a direct application of this above concept.
So that's tau, right?
Sorry,
Tau and
tau is the net torque. You know? So torque is equal to I alpha. I is about that point of suspension or the fixed axis.
IP is moment of inertia, no? Sir?
Okay, so the main thing you have to remember is that at the equilibrium position, the center of mass will be vertically below, okay, the hinge or the axis of rotation. Okay. So in general, if your shape of the object is like this, then where is the center of mass located? You can understand it this way, that this is like the center of mass of the one part of it. Okay, if this is object 1 and this is object 2, this is the center of mass of it. Okay, so both of them, yes, it will be at the midpoint of this line. So this will be where the center of mass of the object is. Okay. So interestingly, this will be at a distance of L/4 from the whole thing, from the corner.
Yes.
Okay, because it's at the midpoint of these two centers. This is L/2 because this is L. So like that. So it will be L/4. Okay. So now you can see what this distance here will be. This distance D will be square root of L/4 whole square
Plus L square.
plus 3/4 L. Okay, now this distance is 3/4 L. No?
Yes, yes.
So L by 4 root of 10. Correct. So when you suspend this like that, okay, what is going to happen is your equilibrium position is going to look like what I'm going to draw next. Okay, so as if this is rotated about that point where it is suspended, such that the center of mass is coming vertically below it. So the center of mass is here. Okay. So this is when the net torque is 0. The moment you rotate this about this, you can see that it's creating a net torque and all that. Okay, so we don't need to again do the whole diagram and the dynamical equation and all that. We just need to understand that time period for small oscillation, for small theta about the equilibrium position. This is the equilibrium position. Time period will be 2 pi under root this, okay, or the angular harmonic motion. Okay. So now moment of inertia about the point P, how we can write that? So moment of inertia about the point P is moment of inertia of the first half rod plus moment of inertia of the second rod. So the first half rod is very simple. It is mass into L square by 3. For the second one, we'll have to use parallel axis theorem. Okay, for the second rod, second half rod, whatever. Okay. So it will be moment of inertia about its own center plus its mass into by parallel axis theorem. Okay. So this is becoming
इसके parallel कौन सा axis होगा?
about with respect to the point P, na? See, it's actually rotating about this axis.
Okay.
So IP is equal to ICM plus MD square. Na? Here that distance is capital D. Have you understood now?
Sir, I'm getting a
Sorry, you are?
समझ नहीं आ रहा कि कैसे वो रोटेट हो रहा है.
See, ये पूरा ऑब्जेक्ट ऐसे रोटेट हो रहा है ना, इस वाले पॉइंट के अबाउट रोटेट हो रहा है. Okay. If it rotates like this, after some time, it's like this, it's like this. Understood now?
Okay.
So now this object is actually doing what? Like just divide it in your mind into two separate objects. So this object is a rigid body whose own center of mass is here, but it's rotating about this point P. Na? Right, na? So that's this diagram here. So to find the moment of inertia about that point P, you're using parallel axis theorem.
Okay. Sir.
ICM plus MD square, but for the second object. Okay. Okay, so this is clear now.
Yes.
Okay, now see how much is D. Yes,
Can you explain how to find IP? एक बार कैसे निकाला एक बार फिर से बोलेंगे.
IP na, that I'm in the process of calculating. Na? See, so
Yeah.
what I've done is I've divided the L shape into two objects, object 1 and object 2.
Yeah.
Each of them are rods of mass m/2 and length L each. Okay.
Yes, sir.
Now see, with respect to that point P, what is the situation of rod 1? Rod 1 is rotating about an axis which is passing through one end of it.
Yes, sir.
So directly apply the formula ml square by 3, but only its mass is not m, it's m/2.
Yeah.
तो understand ना, rod 1 का moment of inertia ये आ गया. Now rod 2 का कैसे आएगा? Now for rod 2 the axis is not in its body, it's somewhere outside. So we don't have the direct formula, we have to use the parallel axis theorem, ICM plus MD square.
Yeah.
In this case I've written it as capital D, so I'll write. Is it clear now?
Yeah.
Okay. And the whole body is the sum of these two rods, no? So the net moment of inertia is the sum of these two.
Yes, sir.
So from here, if I take ml square common,
Or
I have 1 by 24 plus some factor here. So let's calculate the D first. Okay, so D will become L by 4 root 5, right? So this will be 5 by 4 into half. No? So this will become 5 by 8. Just check my calculation once, but looks like
L
this.
by 2 root.
Oh, sorry. Yes, that's correct. But when I square it, I'll get the 4 there. So what I've written in the moment of inertia part is correct, I think. Okay, let's check. Okay, so how much this is coming out to be? ml square, take 24 as the LCM. So 4 plus 1 plus 15, right? 20 by 24 or 5 by 6. Okay, so just check my calculation. Rest it is. So M always cancels out. Okay, when you substitute IP in the formula, obviously IP is proportional to the mass, so it always cancels out. Okay, and you get a term which is dimensionally like L by G. Dimensionally, that is okay.
L by 4.
This value here, and this is sorry, I have written the formula in inverse now. It should be IP divided by MGT. Omega square is actually get for the angular harmonic motion. Omega square is MGT divided by IP. So time period 2 pi by omega. Okay, so this is the expression of time period. Okay, people, so hope this question is clear fully. Okay, now next we move on to. Okay, Jagannath, I'm waiting. Okay, now although we had discussed this in the last lecture briefly, but I'll just take you through the simple pendulum as a special case of physical pendulum again. Okay, so as you know, the simple pendulum consists of a massless thread which is used to suspend a spherical object, a small spherical object called a bob. So since the radius of that small spherical object is negligible compared to the length of the thread, we can treat it like a particle. So if it is given a small angular displacement with respect to this point of suspension, we tend to perform oscillate. So there is two ways by which we can do this. One is we can directly apply the formula for physical pendulum, treating this like a special case of a rigid body that consists of a single particle alone. Okay. So that would be one approach. The other would be a more derivational kind of approach, where since it's a particle, it's actually doing circular motion.
Sir,
Yes.
sir, but in simple pendulum, there will be no small oscillation, right? So
No, here also you'll see that when we do the derivation, you'll realize that the angular harmonic motion condition is only for small oscillations.
okay.
Because otherwise there's sine theta, whereas we want it to be proportional to theta.
Yes.
So if we go with that kind of approach, you can see here that at this position, mg sine theta is providing the tangential acceleration. So that is equal to L alpha whereas T minus mg cos theta is the centripetal acceleration or the centripetal force. Okay. Now in this you can see that alpha is minus d2 theta by dt square. So again the relation that you get is that minus d2 theta by dt square is equal to m by L, sorry, g by L. M cancels out on both the sides. Okay. Sine theta. Okay. And for small theta, so then we get the harmonic motion condition that so the derivational approach is this. The direct formula based approach you can take is that okay for small theta. So here IP, the moment of inertia of this system about the point P, so it is ml square and D is equal to L. That's why I'm saying that you can just treat it like a special case of a physical pendulum where the rigid body just actually is a single particle attached to a thread.
So that's right.
Sorry, Beta, come again. That's
That's MAT, right?
which one, Beta? M by?
Sir, mg sine theta is equal to MAT, right?
Yes, yes, tangential acceleration. ET, yeah. ET is the tangential acceleration, okay, which
Yeah.
is in circular motion. You'll remember the net acceleration is the sum of centripetal acceleration plus tangential acceleration. So centripetal is minus v square by r cap, and tangential is r alpha. So typically, if it is in non-uniform circular motion, the acceleration has both components. Whereas in uniform circular motion, alpha is 0. So there is only centripetal acceleration. There's no tangential acceleration. Okay, now we'll do a example question quickly based on this. So we have a simple pendulum, but it is suspended inside a moving object. I mean, a moving vehicle, which is moving with a horizontal acceleration, uniform horizontal acceleration A naught. Inside this, we have so a simple pendulum is suspended inside a vehicle, initially at rest, and with the pendulum vertical. And now, suddenly, the vehicle starts to move with uniform horizontal acceleration A naught. Okay. So if G is equal to 10 meters per second square and E naught is equal to 0.2 meters per second square, show that the pendulum will oscillate harmonically. Also given the length of the pendulum is, let's say, 2 meters. Okay. Find its equilibrium position in the vehicle's frame. Find the time period and angular amplitude. So it's only the last part which will be a little bit extra something to apply compared to the standard formula based question. The other parts will be standard formula based. So a little bit of concept of, I'll give you a hint here. What you have to apply is the concept of non-inertial frame and pseudo force. Okay, Tanish, I'll scroll up a little later. Just let people start this question, take down the details of the question, then we'll discuss. Okay. Okay, so people, first of all, you'll understand that when you are in this non-inertial frame, once this has started accelerating, there is this pseudo force that is acting on this. Okay, so the vertical is not the equilibrium position. Initially, when this thing was at rest, okay, when the vehicle was at rest, at that point of time, this might have been the equilibrium. This was the equilibrium position. Okay, but now the equilibrium position is going to be at some angle, which is, you can say, anti-clockwise with respect to this. At t equal to 0, when this starts to accelerate, this is the situation. Okay, in this frame, this is at rest, but this is not in equilibrium. Okay, because there is pseudo force weight, and of course there is some tension in the string. So the equilibrium position in comparison will be what I'm showing you here. At some kind of angular position like this, there will be equilibrium.
So we can take tan theta is equal to A naught by G.
Yes, very good. Directly you can do that. Okay.
Sir.
Or you can further take, like that trick method, that in a non-inertial frame like this, it's like effective gravity becomes in the diagonal direction, because it's the vector sum of ma naught and mg is the effective weight, or like the apparent weight. So you can use that method also. So the vector sum of these two forces, mg and pseudo force, when that vector sum aligns with the thread, that will become the position where there is equilibrium. So at equilibrium, this is what should happen. So if this is the equilibrium position, take this as theta naught. So at this position, what should happen? The tangential acceleration should be 0, or alpha should be 0. This is the mean position or equilibrium state. So yes, you can see that is what will happen here, that m a naught cos theta has to balance mg sin theta,
Yes, sir.
or
And
theta is tan inverse of, okay,
A naught by G.
a naught by g. So in this case, you can see that given the value of a naught in radians only, it is tan inverse of 0.02. So that is approximately 0.02 radians only. It's a small angle. Okay. So now you'll realize that this will become your angular amplitude only, because the initial position was at vertical now. So anyhow, so now you'll see that with respect to this angular position, with respect to this equilibrium state or mean position, if you take it to some any angular displacement, then what will happen to your, so now it's like you reorient yourself such that this is your y-axis, okay, because this is where the equilibrium is. This is the mean position. So if you're at some angular position with respect to that on either side, whether you're on this side or on the other side, you should experience torque like this.
Backward.
Okay, or if it's that side, it will experience, okay. So So now what will be the easy way of doing this calculation? Just replace G with effective gravity, which is square root of
A0 square plus G square.
plus G square. Okay. So the time period, so the omega square of your this thing, it will become like G effective by L. The time period will become 2 pi under root L by G effective. So you'll see here that the torque will become this kind of equation you will get where theta is small. Yeah, so in this diagram, you are at an angular position with respect to the mean position. No? It's going to oscillate like this now about the mean position. So it's at theta with respect to this. Okay. So what will happen is what we are doing here is you're taking the vector sum Jagannath of the true weight and the pseudo force. You're taking the vector sum of those two as your effective weight. So that is the method we are employing over here. So this is at theta naught. Okay. And this is your G effective. So in your equilibrium position, you can see your effective weight is acting like this. That's why there is no alpha. There is no tangential acceleration. But at this position, it's acting like this now. So it's having a moment arm. Is it clear now? So at theta with respect to mean position. This is your okay, very good. Okay. So just try and complete this question yourself. Okay. So the time period or omega, both the things you're getting from here, square root of G effective by L. So G effective is square root of G square plus A naught square. So this thing, square root of 100.04, it's very easy to calculate.
Nearly close.
Yeah, binomial approximation you can do. Yeah, Shikhar, the mean position is the position at which the direction of the effective weight is along the thread. Okay. So that it does not create any tangential acceleration with respect to the point of suspension. Understood? No? The vector sum of mg and ma naught is the effective weight which is acting diagonally now. at that angle theta naught. So when the thread is at that angle theta naught, it's in equilibrium. So your vertical for your regular simple pendulum is replaced by that diagonal line at theta naught, okay, which is, yeah. Okay. So your G effective for all practical purposes is still 10 only. Okay. So your time period here, 2 pi under root L by G effective. Technically, it is this. You can take it approximately as much. It's about 2.8 seconds. So we are done with this. We are done with this. Equilibrium is at this much. Okay. Now we have to only find the angular amplitude. So you'll realize here the angular amplitude is that theta naught only, because you're starting from the position at rest, na, which is away from the mean position. So that means you're starting from an extreme position of the oscillation. That extreme position is at the vertical position. So the vertical over here is at tan inverse of A naught by G, or 0.02 radians with respect to the equilibrium position.
Okay.
So what is happening, that this all is telling us that my theta is some angular amplitude, let's say, times sine omega t plus phi. So angular velocity d theta by dt is omega theta naught cos of omega t plus phi. So at t equal to 0, theta will be theta naught sine phi, which is 0.02 radians. Okay. And d theta by dt will be theta naught omega cos phi, which is 0. So from this you can see that and phi will be pi by 2.
Sir, how are we getting phi is equal to pi by 2?
Because see, these two equations, now what they are showing you is that sine phi is positive,
Yes.
and cos phi is 0. That's only possible when phi is pi by 2.
Okay.
सर तो SHM में कैसे प्रूव करेंगे?
वो तो we have done above, na? This torque equation, no?
You just have to satisfy the torque equation, right, to prove
We have,
Yeah.
yeah, from here we proved, na, that is angular harmonic motion. Okay, so angular amplitude. Okay, people. So hope this is clear. Okay, so now we move on to another type of pendulum, which is called the torsional pendulum. Now this is completely different to physical pendulum. So a torsional pendulum, basically any rigid body, can be like a disc even, which is suspended using what is called a torsional wire. So torsional wire is an sort of a massless thin wire, but it has the property that when it is twisted, it applies a restorative torque. So that is a property of any material actually. If you twist it, it tends to restore back. But the torsional wire has a property that when you twist it, it applies a restorative torque which is proportional to the angular twist. Okay. So torsional wire, it has the property that when twisted or rotated, it applies a restorative torque where K is what we call the torsional constant. Is a mechanical property.
Sir,
Yes.
what's the difference between a torsional wire and a normal?
A normal wire, when you twist it, it will tend to either get permanently deformed, or even if it applies a restorative torque trying to restore back to the original position, that restorative torque will not be proportionate to the displacement, to the angular displacement. Okay. So if you twist this through an angle theta like this, that wire on its own applies a torque like this, and that torque is proportional to theta. So that is the property of the torsional pendulum or the torsional wire. You can think of the torsional wire as an angular version of a spring. Like when you displace a spring by x, it applies a force minus kx. So like that, when you give this an angular displacement theta, it automatically applies a restorative torque of minus k theta.
Okay.
Understood? So in this case, if this rigid body attached to a torsional wire like this has moment of inertia, I, okay, then see that this is an angular harmonic motion with a time period of angular harmonic motion with omega square k by m, sorry, k by I, where I is the moment of inertia. So time period is 2 pi under root I divided by k. Now notice here, even though we use the symbol k, this particular constant has different dimensions compared to spring constant. Here the dimension of k is dimension of torque divided by angle. So dimension of torque is force into length, and angle is dimensionless. So it is, this k is in Newton meter, whereas spring constant k was different. It was in Newton per meter. So now, for example, very standard type of question. If we have a dumbbell shaped object, which consists of a massless rod of length L and two identical particles of mass m each. Now this is suspended from the midpoint using a torsional wire which has a given torsional constant. So the dumbbell consists of two identical particles attached by a massless rod. Now this dumbbell is suspended from its midpoint by a torsional wire. This torsional wire has of torsional constant, let us say 12 Newton meter. So we have to find the time period for angular harmonic motion. So if twisted by 0.4 radians and released from rest, find the time period, angular amplitude, for its angular oscillations, and also find the maximum speed of each particle during the oscillation. Okay, so you'll realize that this dumbbell will be oscillating about this kind of an axis. It will be going like this and like this, back and forth. So the two particles will be doing angular motion, or they'll be in a circular path in a horizontal plane, but going back and forth, not completing a circle. So as they go back and forth, they will start and stop, start and stop. So at the mean position, they will have the maximum kinetic energy. So maximum tangential speed. So just try out this question, people will discuss.
So can you please show that torsional pendulum part?
Yeah. Yeah, Jagannath, the dumbbell is rotating. Okay, so when you twist the torsional wire, the dumbbell rotates with it, but the torsional wire now applies restorative torque. No? So the dumbbell has a tendency to get restored back to the position it started from. In the process, it oscillates. So this is just like an angular version of your spring mass system. No? What happens there in terms of linear motion, the moment you disturb the block from the equilibrium position, the spring applies restorative force, and potential energy is converted to kinetic and back and forth, and there's a linear harmonic motion. So SHM. So like that here, the moment you twist it from that equilibrium position, there is a restorative torque, which is proportional to the displacement, the angular displacement. So when you twist it, you have stored elastic potential energy in the wire, torsional wire, and that gets converted to rotational kinetic energy of the dumbbell, and back and forth, the energy oscillates.
Sir, can you show the full question?
Sir, wait, sir. Sir, so that's angular HM, right? Not SHM. Sir,
Oh, sorry. I'll scroll down to the question. Okay. So now you can see that when you twist this through an angle theta, this applies a restorative torque like this. Okay. So torque is equal to minus k theta, and that should be equal to moment of inertia into alpha. So we have d2 theta by dt square is equal to minus k by I theta. So you have the ready-made formula. Okay, you just need to find the moment of inertia and substitute the values. Okay. So now moment of inertia is for this dumbbell-shaped object about this axis. So what will be the moment of inertia? Its length is L. So I will be equal to 2 times each particle is at a radius of gyration of L by 2. So it's how much ml square by 2. That is our moment of inertia. So time period is becoming 2 pi under root ml square by 2k. So let's put in the values and find this now. So each particle is 1 kg. L is in meters this much. And K was how much? 12 Newton meter. Okay. So I think here 12 will become an unnecessarily large value. I'm just changing the value of this so that it's more easy to calculate. Okay. So I will just make it 0.02 Newton meter. Because the size is also small, not 20 centimeters. So we don't want that much of torque. Then it will rotate very rapidly. You'll see the time period is just becoming 2 pi with this, I think. Seconds. So now it's beginning a very slow rotation. Okay. And omega equal to 1 radian per second. Okay. So you're done with this time period and all. Now we have to find the maximum speed of each of the particles. So just visualize the motion of this dumbbell in that horizontal plane. You will see it rotating back and forth. So you'll realize that maximum speed will be at the mean position. Okay. And just use the concept of circular motion that the tangential speed is equal to radius into angular speed. So angular speed is what? D theta by dt. So this will also become important, this statement here. Because from this you will get the angular amplitude. Okay, so now let's look at the back and forth motion of the dumbbell. So if we are taking the top view, okay, of this, so we will see the dumbbell, rotate back and forth like this. So let us say this is the mean position. So these are the extreme positions. So when it's at the extreme position, it's at rest. Whereas at the mean position, it is at maximum kinetic energy state. So it has either this type of motion or this type of motion. So theta is equal to theta naught sine omega t plus phi, where omega we've already calculated. It was square root of I by k, which came out to be 1 radian per second. Okay. Now we also see that this means that the angular velocity at any point of time d theta by dt is omega theta naught cos omega t plus phi. Now it was given that at t equal to 0, we had twisted the object through an angle of, I think, what was it, 0.2 radians. Sorry, 0.4 radians, and released it from rest. Released it from rest. So once again, it's that kind of situation. You can see that from this first equation, theta naught sine phi should be equal to 0.4 radians. And from the second equation, omega theta naught cos phi should be 0. So from these two equations, you will see that phi is again pi by 2, and the angular amplitude is 0.4. Now again from this, you can see that the maximum angular speed at the mean position is equal to omega into theta naught. So that in this case is 1 radian per second into 0.4 radians. So don't get confused that the unit is becoming like radian square per second. Radian is dimensionless. So the important thing is it has the dimension of time inverse. So 0.4 radians per second. Radian is a dimensionless unit. So this is the angular speed. So if that is the angular speed at this thing at the mean position, then what will be the mean speed of each of these dumbbells? So or 4 centimeters per second. So the maximum speed that they experience is 4 centimeters per second. whereas the maximum angular displacement to which they go is 0.4 radians. So that is how the motion of that dumbbell will look if you're seeing from above, okay, or from below. In a horizontal plane, it will be twisting back and forth, clockwise and anti-clockwise. And as it is doing that angular oscillation, every time it passes through the mean position, it has the maximum kinetic energy. So the dumbbell has maximum angular speed, and therefore, okay, the individual particles of the dumbbell have maximum tangential linear speed, L/2 into the angular speed. Is it clear now, Jagannath? As your torsional wire is twisting clockwise, anti-clockwise, your dumbbell is rotating in the horizontal plane. No? So therefore, if you see it from above or below, this is how it will look. Yeah, Shikhar, the highest speed, the maximum speed for the dumbbells will be when, I mean, for the particles individually, will be when the dumbbell has maximum angular speed. No? Is it clear? So maximum angular speed for the dumbbell will be at the mean position. No? So we have written theta as a function of time, where we know the angular amplitude. So we know the angular speed by differentiation, d theta by dt, that equation we've written. So in that you can see what is the maximum angular speed. It is omega into theta naught. No? So at the time when that dumbbell's rod is rotating with angular speed of that much, we can calculate the linear speed of each particle because it's a circular motion type path. So r omega. So r for each particle is L/2. No? So that's how we got the Vmax for the individual particles. See the diagram at the lowest part, you will understand. Okay, when the rod is rotating with d theta by dt equal to that value, 0.4 radians per second at the mean position, at that point of time, each of the particles will have maximum speed of L/2 into that 0.4 radians per second. Okay, good. Okay, so just complete noting this down. With this, we conclude today's session, and basically we're done with all theoretical concepts and formula and all that of SHM. So, but there is a lot of variety of questions, as you would have seen in HC Verma also. So we will take up questions in the next lecture. We'll do questions and discussions. Okay. And if you have any doubts, we can see some of those doubts in the next lecture also.
Thank
The
you,
thing
sir.
is like, okay, there is a lot of core mechanics involved when you are doing these type of questions. There are concepts from rotational mechanics, rolling, work energy if required, constraint relations, all these things put together. So be patient while you're doing the questions. If you get stuck in any mechanic steps, you can just send it to me. I will give you some hint, etc. Okay. So that's it for today's session. People, wish you all the best. Thanks for attending.
Thank you, sir. Bye, sir.
Thank
you, sir. Bye.
Bye, sir. Have a nice day.
you, sir. Bye.
Okay, bye, people. Have a nice day.